Hello, I'm Vivek Kwatra, and I'll talk about stabilizing first-person 360-degree videos. And this is joint work with Chetan Arora. So 360 videos like these are obtained using special cameras that are able to capture the full spherical 360-degree view around them. And these cameras are now available in consumer form factors, handhelds, which is great because all of us can now capture 360 videos. But one problem is that often these videos tend to be shaky. And this is especially a big problem when we try to view these videos in VR because it can actually cause physical discomfort and sickness. It has a term of its own called cybersickness. So how do we solve this problem? And I'll start by talking about some prior art. So there's a paper by Johannes Koff in 2016 on 360 stabilization, which starts with a cube map representation of the 360 video, which is helpful for computing feature tracks, which are then fed into their system, where they first compute 3 rotations or orientations for each frame in the video. And that's sort of one of their key contributions, but what I'll talk about is the stabilization part. So once they have these 3D orientations, they try to stabilize it. And their stabilization basically works by derotating all the frames so that they are aligned with the first frame. So essentially, all frames are aligned to a global reference orientation, which means the camera eventually points in the same direction throughout the video. Now, this is great for stabilization, but one problem with that approach is that it does not preserve the intent of the videographer. So in this case, the jogger is actually turning around the block, pointing the camera to the front, but you can see in the bottom, which is the stabilization result, the jogger is now in the frame of the video. So it's changing the orientation with respect to the jogger. So our approach is to address this problem. And the way we do it is, instead of having a single orientation for the entire video, instead we try to find a curve which basically is smooth, but at the same time as close as possible to the original camera path. And we do this using a constrained optimization approach, which is inspired by some of our prior work on 2D video stabilization. So what we do here is we represent the stabilized path, which we want to compute, as a composition of the original shaky path, which is R here, with an orientation update denoted by B. So this orientation update is an orientation transform that you apply to every frame, and this is what you compute during the optimization. And the objective of this optimization is to smooth the eventual path. And we express that using minimization of time derivatives of the path. So I'll talk about, you can have like different orders of these smoothness here, but I'll talk about 2 terms here. So the green one shows the first order smoothness. And what it tries to achieve is to fit horizontal lines to the path, which effectively is trying to look for a constant orientation in the outcome. And this is pretty much also what you get with the result of Koff's work. If you look at the second order smoothness term in yellow, that one tries to actually fit straight lines, but of arbitrary slope. So this actually gives you more freedom in how the path can actually take shape. The other ingredient here is the constraint itself. And that is expressed as a threshold on the orientation update angle. So if you look at the animation here, you'll see this green envelope developing, and that is basically controlled by what is your threshold. So the larger the threshold, the larger this envelope, and it gives you more sort of freedom in where you put the stabilized path. Of course, after some threshold, you kind of start losing in terms of how much stabilization you can achieve. And one observation we made here was that if you express your orientation in quaternion space, then you can translate this threshold simply as a lower bound on the first term of the quaternion, which makes the optimization problem easier to formulate and solve. So here are some results on time series plots. So these are from 2 actual sequences. Blue is the original shaky path, and the orange is your stabilized path with an upper bound of 1 radian. As you change the upper bounds, you get different paths shown by these different dashed lines. And here are some qualitative results. And on the top left, I'm showing the original shaky video. I'm showing our result at the bottom, and the top large result is Koff's result on the same video. So as you can see, we are stable. Koff's result is also stable, but we are able to maintain the orientation that was originally intended in the video. And this is another example where the person actually takes a U-turn, and we again take the U-turn with the person and keep the video stable, whereas in the Koff's result, it almost looks like the camera is sort of walking away from the scene. Here I'm just displaying some feature trajectories to show the sort of quality of stabilization we are able to achieve. As you can see, the trajectories are much more smooth in the bottom result. And finally, I want to show that we can also apply the same technique for narrow field of view videos because we can compute the orientation and we can stabilize them. So if you have more questions, we can talk at the poster session. Thank you.